Hello and welcome back. We are going to be starting on the topic of equilibrium today. And really the most important thing to think about equilibrium is this. When we wrote reactions in our first semester of general chemistry, we write a reaction that says, A plus B goes to C. And we'd ask questions, if I have 5 grams of A, how much C can I make? Or if I had 18 grams of B, how much C could I make? Or, a limiting reactant problem that says, I've got 5 grams of A and I've got 18 grams of B, how much C can I make? And we did that, but the assumption underlying all of that was that the reaction went to completion. That no matter what happened, you'd either use up all your A or you'd use up all your B, and the reaction would only stop when that was done. And in this equilibrium chapter, we're going to challenge that assumption and say, hey, that's actually not true for most reactions. Most reactions don't go to completion. They undergo equilibrium. So we're going to talk about all that and how to think about it, and then obviously the math of it, since we love math. So we're going to talk about the equilibrium constant and the fact that it really is constant, which is such a neat thing. I mean, it's crazy, and we're going to find that no matter what we do, no matter what concentrations we start with, or what we try to do to reaction, we're always going to be able to calculate this thing about it that's constant, and it helps us to solve some neat problems. We're going to express it in units of concentrations and units of pressures, because sometimes we deal with one, sometimes we deal with the other, and also figure out how does that change when we have solids and liquids present, because most of the work we're going to be doing in here is either gaseous or it's going to be in the aqueous phase. That's why we have concentrations. But what happens when we have solids and liquids? Then we talk about this thing called the reaction quotient, which is exactly the same thing as the equilibrium constant with a different letter. And it's not just to confuse you. There's a good reason for it, but that's all the reaction quotient is. And we're going to find concentrations at equilibrium from initial conditions. And that's going to take the bulk of our time. That one line right there is probably the bulk of our time for the next, 8 weeks of the semester. So it's a huge thing that we're doing, is finding these equilibrium concentrations based on initial conditions. So we're going to work really hard on that. And we're going to see it over and over again with just different letters here and there, just to try to confuse you. No, it's not the point. It's not to try to confuse you. It's just because we're going to talk about different reaction types, and so we kind of specify things, but we'll see that as we go. And lastly, we do Le Chatelier's principle, which you may have run across before, which just says how a reaction responds to change. So that is our schedule in the equilibrium chapter. So like I said, we've always assumed that if you have this reaction, that it always goes to completion. You have your blues, you have your purples, and as time progresses in this direction, eventually what's always going to happen is you're going to end up with everything possible being products, and you're going to end up either with no blues or no purple squares left. In this case, they were equal and they were balanced out, and so we have neither of them left. We just have the mixed ones there. But it turns out that, like I said, it's not really true. What most reactions do, not even some reactions, most reactions, is they come to what's called an equilibrium, which means as they react, we start off with just circles and squares. So we do start off with just our reactants. We're going to even challenge that later on. But we do start off with just our reactions, and as time goes on, we start to produce product. And so we make some of our product. But then we find that no matter how much time we wait, we have essentially a constant amount of product, and we essentially have a constant amount of reactant that's still left. And this is forever. There's no limit. There's no like, if I just wait long enough, I'm eventually going to make all product. It doesn't happen. You get both going on at the same time. And so how we notate that is we use these double arrows here. So instead of saying we just have this one arrow that everything's going to the right, we use the double arrows to say that this reaction, even at infinite time, is at equilibrium. In fact, all reactions in infinite time are at equilibrium, but we're going to find that some reactions are so far towards one side or the other that we count them as going completely. But all reactions actually are at equilibrium. And a lot of them are at equilibrium where you have lots of concentration of reactants left over and lots of concentration of products left over. And it stretches the definition of reactants and products. But we'll define, and I'll talk about this again later, is that reactants is literally just whatever you write on the left-hand side of your reaction arrows, and products are just literally whatever you write on the right-hand side of your reaction arrows. And that's it. That's all the actual definition of reactants and products that you're going to get. My children outside are very excited about that definition of reactants and products, so I hope you can still hear me. So that is what we're going to be talking about. How do we calculate things? How do we predict things in this kind of scenario? Okay, So again, just to be clear, what do the double arrows mean? It means that both reactions are happening. That if we have this reaction, that at equilibrium, when we look at it, nothing's happening. When we look at it, it's just sitting there. But at equilibrium, the blue things and the purple things are making that combined one. Our reactants are making our products. But also, simultaneously, the products are turning back into reactants. And so the products, the little blue and purple thing, are going back into the blue balls and the purple squares at the same time. So what we call kind of a static equilibrium, we look at it, we're like, wow, it's as exciting as watching grass grow, is actually actively dynamically doing things on a molecular scale. Things are falling apart, things are forming, but they're doing so in a way that objectively, macroscopically, we can't even see what's going on. An example of this is if you take a big beaker of water and you pour in a ton of salt. So you pour in just a ton of salt, right? And if you pour in a ton of salt, eventually you're just going to end up with this pile of salt at the bottom. Certainly some's going to dissolve and you're going to have some ions in here, but you're mostly going to have just this big pile of salt at the bottom. And when you look at it, it is very unexciting. You're just staring at it, you're like, wow, there's nothing happening. There's a pile of salt. And there's some salt dissolved. I can taste, don't taste things in lab. That was not good. Okay, but you taste right if you do it at home. So it's salty. But looking at it, nothing's happening. But if we were to examine the surface of that salt and blow it up really big, and we see that there's these sodium ions and these chloride ions. Remember the anions are a little bit bigger. And they form this kind of regular structure in 3 dimensions, which we can't really do here. Well, we can. I'm just not very good at drawing, so we're not going to. Right. So they form this kind of regular grid of sodiums next to chlorines, and each one surrounded by a bunch of different ones. And then the water is out here. And if we actually look at the surface of this, constantly there are sodium ions being tempted away and going off into the water. So sodium ions are dissolving into the water. Chloride ions are dissolving into the water due to the polar nature of water. But at the same time, there's other sodium ions in the solution and chloride ions that are actually globbing back on to the solid. And if you waited long enough, both the texture and the shape of the solid would change over time because there is a little bit of stuff going on constantly. And that's what we mean about equilibrium. It looks like nothing's happening. From a concentration standpoint, nothing's happening. The concentration of that salt is staying the same. The salt in the water, is staying the same no matter what I do. But on a microscopic scale, things are still changing. Reactants are forming products, products are forming reactants, and so there actually is what we call a dynamic equilibrium. Most people think of equilibrium as static, but there's actually a dynamic equilibrium where things are constantly reacting with one another. So what we're going to do is we're going to plot that because we love to plot things. So it just gives a chemist joy to plot things. So we're going to plot concentration versus time. And let's go ahead and use red for our reactants. So let's put a little key here. Oops. Reactants. And we'll go ahead and use orange. No, we'll use purple for our products. So we're going to kind of keep things simple for now, and we're going to say, hey, let's assume we started with all reactants. Okay, so we have 100% reactants at the beginning. We have absolutely no products. So at the very beginning, our reactants are going to be up here at their, I thought I tapped my color. The reactants are going to be way up here at their highest possible concentration. The products are going to be down here at 0 concentration because we don't have any of them yet. And as time progresses, again, what we've always assumed is that the reactants eventually go to 0. Right? They eventually go down here to 0, and the products go up to their maximum. But what we're saying now is, no, it doesn't have to go to 0. It just has to go to some steady state at equilibrium. And so it's not going to look like it goes all the way down to the axis. It's going to look like it goes somewhere here. And you can see it kind of flattens out there at the end, where the concentration of my reactants is no longer changing. It's still happening on a microscopic scale that reactants are making products, products are making reactants, but on a macroscopic scale, the overall concentration isn't changing. So if we plot our products, right, we start with 0, we're going to make some, and it's going to look something like that. And so we can see that as we wait, There's eventually some products, but not 100% products. It's not making as much as possible. And there's still some reactants. And there's this point at which neither of them are changing. And that point where they're not changing anymore is what we call equilibrium. Everybody always wants to know, what does this point mean? That point means absolutely nothing. There's no reason to think about that point as special. It looks special, right? Because it's the intersection of those two lines, but it just happens to be where their concentrations are equal, but it actually has no significance. What has significance is when these guys go from curving, from changing over time to constant over time. And where exactly that is not important, but I'm going to say, hey, it's somewhere right about there. And this is what we call the point of equilibrium. When we've reached this point, we have reached the state where macroscopically there's no change in concentration of our reactants or our products, but dynamically on a microscopic scale they're still reacting, forming products, forming reactants. But concentrations are constant. Okay? So that's what concentration versus time looks like. Now let's change it and let's look at rate versus time. Rate versus time, well, if you have a lot of, and what did we use for our colors? We used a red for our reactants, so let's be consistent. Reactants and products. And this is just an example. Obviously, we're not plotting anything real here. We're just thinking about it. And if you have a lot of reactants at the beginning, they're going to react very, very quickly. Right? So you're going to get a lot of reactants reacting. But imagine towards the end when you don't have very many reactants left, they're probably going to be reacting a little bit slower. And so you're going to find that this rate of reactants starts off fast and then levels out, right? We said on a macroscopic scale, it doesn't look like anything's happening, so it's probably going to be leveling out. But what about the products? The products, well, if you don't have any products to begin with, what's the rate of the products reacting? You're like, products don't react. Yes, they do. In an equilibrium situation, reactants are making products, that's a reaction, and products are making reactants, and that's also a reaction. So we know that at the beginning, because we said so, we don't have any products, so the rate of the products reacting must be 0. But as you start to make products, the more and more you have, the more and more are going to react, and you're going to find that this goes up over time until that happens. And what happens here? This is again the point of equilibrium. And to be clear, everything after that is also equilibrium, but this is the point at which they reached equilibrium, is when the rate of reactants making products is equal to the rate of products making reactants. So that's really a definition of equilibrium. Equilibrium. My brain couldn't spell it for a moment. Equilibrium. When the rate of reactants making products is the same as the rate of products making reactants. That's when we are at equilibrium, when the forward reaction and the reverse reaction are at equal rates. And we kind of mentioned that when we talked about mechanisms in the kinetics chapter. We said, hey, those equilibrium things, let's say those two rates are going to be equal to each other. Okay, so this is the actual rate, molar per second or molar per hour or whatever units you're using for your rate. All right, so that is an important thing. It's not when the concentrations are equal. It's not when the concentrations are equal when we've reached equilibrium. It's when the concentrations aren't changing and the rates are equal. Imagine burning a piece of paper. If you take a piece of paper and you burn it, it burns until all the paper's gone. That's the equilibrium for burning paper, is there's essentially no paper left and there's all smoke, ash, soot, whatever you want to call it. Okay? So there, the concentrations aren't equal. It didn't stop when half the paper was burnt, but it did stop when there was no more paper left. Okay. So here's a question for you. At equilibrium, what is true? The concentration of products and reactants are equal. The total mass of products and reactants are equal. There are always more products than reactants. And the rate of product formation equals the rate of reactant formation. All right, what'd you come up with? Well, hopefully in this whole conversation you said, he just talked about the fact that concentrations don't have to be equal. So it can be, it's highly unlikely, but it can be that the concentrations are equal, but it's not a requirement of equilibrium. The total mass of products and reactants are equal. Well, I was reading this as I was doing it. I said, oh, I probably didn't phrase that well. So, if you came up with B, I could totally understand what you mean from a conservation of mass perspective. What I meant was the total mass of products and the total mass of reactants are equal. So, I've got 5 grams of reactants and 5 grams of products. So if you came up with that one, we're going to call that one okay, as long as you were thinking of conservation of mass. There are always more products than reactants. No, right? There are reactions where pretty much nothing happens. Everything just stays as a reactant. For example, if I try to burn a rock, right? Rock plus oxygen, not much happens for most rocks. Okay, there pretty much everything stays as reactants. The rate of product formation equals the rate of reactant formation, and that's the one we said, hey, that's kind of the definition of equilibrium, is when those rates are equal to each other. So hopefully that was helpful. Next, we're going to talk about how do we quantify this? What kind of math can we do with this? Hope that was a good introduction to equilibrium for you. Bye-bye.